Hello everybody. In this video, we are going to talk about non-recursive predictive parsing, or which we commonly also know as LL1 parsing. Now, in our previous lectures, we have also seen recursive descent parsing, which is the type of top-down parsing, where we follow recursive procedures to complete our parsing. But we have seen that recursive parsers are quite slow, so we would like to have a parsing technique which is easier or more faster to implement. So for this we have under top-down parsing, we have our non-recursive predictive parsing. So let's see what it is all about. So LL1 parsing, this is a type of a top-down parser, and it is predictive. Predictive means we look at the next input symbol and then we predict which production rule is to be used. And for this, we use a table. That's why predictive parsing is a table-based parsing. And I have already mentioned in our previous video that LL1 here, 1 here stands for the number of look aheads, the number of symbols which we will see in the input, and then we will make our prediction. So LL1 stands for we are going to have 1 look ahead symbol. So LL1 parsing is a top-down parsing, it's a predictive parsing, and it has got 1 look ahead symbol that we will see, and then based on that our predictions will be based. Also, this is a non-recursive parsing. So instead of making your recursive function calls, we are going to use a stack for the purpose of parsing. So in the parsing, in LL1 parsing, we create a table which looks something like this. The parsing steps, we are listing it out here. So if you see, the first column is the step number. So this just lists out serially the steps so that we can refer to that later. Then next comes your stack. So the second column shows the contents of your stack. So you can see one special symbol here, $. So dollar is the symbol which we use at the bottom of the stack. The first element at the stack is it contains the $. Then this is followed by, you can see there is a symbol here S. Okay, so this is the start symbol. Okay, so we keep on pushing elements to the stack. Okay, and the contents of the stack, you can see it from this column. The third column is for the input. So we write down the input in a left to right manner. So our input in this example here is parenthesis, parenthesis, and at the end of the input, we have a $ symbol again, which marks the end of the input. So at every step here in this column, we are going to show what is the input which is remaining to be passed. In the second column, we are going to show at each step what are the contents of the stack. And the last column out here, the fourth column, this shows the actions that are taken. So what are the possible actions? Possible actions can be, we replace a symbol on the stack with its expansion. That is, we expand it based on a production that it matches. Or if it is a terminal symbol, then we see if it matches the symbol at the input. And if there is a match, then we take some action. So we will see that all these steps are listed, the actions are listed according to the steps. So there are basically 2 actions. First is generate. So the generate action, what it does, it replaces a non-terminal, say A, which is at the top of the stack, by alpha. Now, what is alpha? Now alpha will replace if the production chosen that we have selected is A derives alpha. So if I have something like this, if I have a production like this, and the non-terminal symbol at the top of the stack is A, and I choose that I'm going to use this production, then I can replace A by alpha. And this is the generate step or generate action. The next action is match. Here, what we do is, if the element at the top of the stack is a non-terminal, then we use generate. But if the element at the top of the stack is a terminal symbol, then we try to match it with the next input symbol that is there in the input column. So if it matches, then we say it's a match. If it does not match, means we are in trouble. So that is an error, and the parsing will halt. Parsing will stop. So two possible actions, generate and match. And so the parsing process starts like this. First of all, we push the start symbol to the stack. Remember, the stack already contains the dollar symbol. Then we start by pushing on the start symbol to the stack. Then what we do, we carry out the various actions one by one. Okay, and finally, if the input and the stack both are empty, means the stack also is empty. Empty means it contains only the dollar, and the input is also empty, so the input also contains dollars. In that case, we say that the string has been parsed successfully. So we say that it is an accept. So these are the steps. So let's see with an example. So my grammar, you can see here, it's a very small grammar, matching of parentheses. So I have one symbol only, S, and the two productions I have, S derives parenthesis, S, closing parenthesis, followed by S. And the other production is S derives epsilon. So we start the parsing. The stack contains dollar, okay, and we push the start symbol to the stack, to the top of the stack. So we start with the start symbol here. And what is the input that I'm going to be parsing? It is this, parenthesis, parenthesis. A simple one with parenthesis, parenthesis. And the end of the input is marked with the dollar. So now if you see the element at the top of the stack, okay, everywhere you see that this dollar, this is the bottom of the stack and this is the top of the stack. So in the top of the stack we have a non-terminal S. So that means we have to apply a generate action. So which generate action we'll use? Suppose we decide that we are going to use this production. S derives parenthesis S parenthesis S. Okay, so this is the action that we are going to do. So what happens once we take this action? The content of the stack may change. The contents of the input may also change. So let's see what happens. In such a situation, when we are using generate, then the element at the top of the stack, A, say this is A, is replaced by A derives alpha. So our alpha is what? Alpha is parenthesis S parenthesis S. So we are going to replace this S at the top of the stack with parenthesis S parenthesis S. And remember, this is a stack. So we are going to add the items are going to be added, are going to pushed in from right to left. So this is how, after pushing the stack contents, this is how the stack will look like. So I have first what will go inside, this S will be replaced, this S will no longer be there, it will be popped from the stack, and this part, which is our alpha, will be pushed to the stack. And how? From which side first? First from the right. So first S will come, so S appears here, then this closing parenthesis comes, so closing parenthesis comes here, then this S will come, so this S appears here, and finally the opening parenthesis. So finally opening parenthesis. Okay. So what we have done a generate. So in generate we have used this production. So start symbol is replaced by this. Now look at the input string. Input is not, we have not consumed any input. In a generate, we do not consume any input. Now we will see at the top of the stack. Now I have this opening parenthesis. So it's a terminal symbol. So if it's a terminal, we are not going to look at generate, we are going to look at match. So we are going to see if this symbol matches the first symbol in the input. So it matches. So this is also opening parenthesis. This is also opening parenthesis. So we are going to match these two. So let us now, it matches. Yes. So action is match. So what we will do now, we will remove this from the input symbol, we will input column, we are going to remove this non-terminal. Similarly, from the stack also, we are going to replace this, remove this terminal. So this is how it's going to look like. So now after this symbol is removed, I am left with S, closing parenthesis S, and input also we have already consumed one input, so it is now closing parenthesis and $. So now again I am left with a non-terminal at the top of the stack. So now again I have to generate. The action possible is generate. So again now here we decide the which production rule we are going to use. So we say we have decided here that we are going to use S derives epsilon. Remember, this is our grammar. So S derives epsilon. So epsilon means it is not going to be replaced by anything else. So it's going to look like this. Okay, S closing parenthesis, and this S is replaced by epsilon. Okay, input symbol, we have not consumed any input symbol. Now look at this. Top of the stack is a terminal symbol, closing parenthesis. Does it match the input? Yes, it matches the input. Yes, so match. Action is match. Next. So this two will go. We are left with $S and dollar here. Okay. Now again, I'm left with a non-terminal at the top of the stack. So we are going to generate. So generate S derives epsilon. Okay. So once we do that, I'm left with $and $. And remember what I said, that when you're left with an empty stack and an empty input, it is except. So we have accepted the input string parenthesis parenthesis. So this is simple matching of the grammar here is simple matching of parenthesis. So this is how the parsing takes place. Now output of the parsing phase is not just whether it is accept or reject. Okay, when will it be, before I go to the next, when will it be a reject? Suppose I'm left with something here on the stack and my input is empty. Then it would be a reject. Or I have something in the stack, or I have something in the input but my stack is empty. Then also it would be a reject. Okay. So here I have in this, these are the parsing steps. This is how parsing is done. But the output of the parser is also the parse tree. So along with the actions that we have here, we can include the parse tree construction steps also. This should not be none. It should be add a node construction actions. Add node construction actions as each non-terminal or terminal is pushed onto the stack. So whenever you are pushing something into the stack, you construct a node for it. Okay, in the tree, parse tree. Again, we'll see for the same example, we'll see how this is done. So for the parse tree construction, every action, whenever you're pushing something onto the stack, you generate a node for it. So for the same one here, the stack it contains S. So we start with the node with S. We have pushed S to the stack. So S will create one node labeled S. Then here what we have done, we have generated, we have pushed these symbols into the stack. So we will construct this a node for each of these, and these nodes will be connected to the parent, the one which has been replaced. Okay, that will be the parent. So S here has been replaced by all these four. So 4 nodes created. for every terminal and non-terminal, and for each of the four, the parent is the one which has been replaced. So S. Next step, I have replaced this parenthesis. The parenthesis, okay, no, not required. So here I have S. S is replaced by your epsilon. Okay, so this production we have used. For the next one, okay, it remains the same because it's a match. So match we are not doing anything. Only when we are doing a generate. Okay, so whenever we are pushing something to the stack. So here S derives epsilon. So we have basically what we have done is we have replaced S by epsilon here. So this is the parse tree. So finally what you get here, this is the parse tree for this parsing process. Now in the parsing process, we have checked the next input symbol, we have checked the element at the top of the stack, and then we have made a decision as to which production rule is to be applied. Now how do we make this decision? In our example grammar, we had two production rules. One was S derives parenthesis S, closing parenthesis S, and the other one was S derives epsilon. Now how do you decide which production is to be used? Okay, so that is done with the help of something called the parsing table or the LL1 parsing table. So the decision needs to be made as to which production is to be used to replace a non-terminal at the top of the stack. So you look at the terminal at the non-terminal at the top of the stack, you look at the next input symbol, and then you make the decision. And this is made simple with the help of this table, that is the parsing table. So the parsing table is constructed like this. You have for every non-terminal, you have one row. For every non-terminal, you have one row. And for every terminal symbol, you have one column. And you have one additional column for the special marker, that is the end marker, that is dollar. So how do you interpret this? In our example grammar, it had only one non-terminal S, so we have only one column in our parsing table. And there were two terminal symbols, open parenthesis, closing parenthesis. So we have two columns, plus one column for the dollar. So how do you interpret this? This table can be read like this. So if the element at the top of the stack is S, and our next input symbol is opening parenthesis, then use this production. If element at the top of the stack is capital S and the next input symbol is closing parenthesis, then use this production. Okay? Or if S is the non-terminal at the top of the stack and in the input you have dollar, that means you have finished reading the input, then use this production, S derives epsilon. So with the help of this parsing table, all you have to do when you have to make a decision as to which production to be applied, you would have a look at this table and then you can decide which production is to be used. Something about LL1 grammar that we should know is that not all grammars are LL1. So if a grammar is LL1, for a grammar to be LL1, every entry in the parsing table, that means every cell in the parsing table, must have only one production. At the most, it can have one production. So that means if there is one symbol at the one non-terminal symbol, and by looking at the next input symbol, you should be able to decide as to which production is to be used. If you have multiple entries, if you have more than one production for each entry, in that case, you will have again to make a decision as to which one to apply. So you will not be able to use the parsing algorithm for LL1. So for a grammar to be LL1, The parsing table should contain at most one production for each entry. Okay, so this is one rule. Other is, of course, the grammar must be non-ambiguous. If it's an ambiguous grammar, you have to rewrite it. Also, the grammar should not be less recursive. So any less recursion has to be removed. Also, LL1 grammar must have less factoring. You should all do less factoring before you can construct the parsing table. So, in LL1 grammar, you should check first if it is a LL1 grammar. First of all, you must check if it is non-ambiguous. You must check that there is no less recursion, and then you must check that less factoring has been done. Only after that you can try constructing the parsing table. Once you have constructed the parsing table, if one cell, that means one row, one column, if one cell contains multiple productions, that means the grammar is not LL1. So you cannot have a LL1 parser for that table, for that grammar. Okay. So these are certain things that we will see in the next few videos. Okay. So that's it. So in the next video, we will be discussing about construction of the parsing table of LL1.